Okay. Yeah, any questions before we talk about today's lab? Or if not, let's get started. So as I mentioned, I sent out the email early today. So please check the introduction video for today's lab. I think that video is very helpful. Okay, so all right. So today you're going to measure the inductor and the capacitor again. So today is about step response and the timing circuit. And the timing circuit is the 555 timer. I think you already play with or you already checked the schematic for the timer in the pre-lab. Okay. The timer is a very useful chip. Okay, so let's talk about the task 1 and task 2 first. So again, you're going to measure the capacitance and the inductance manually. So task 1, you're going to build something like this. Okay, this is the circuit you're going to build for task 1. So you're going to generate a square wave. Okay, so maybe you will use W1 from your AD2 to generate a square wave. And then the W1 is connected to our sense, and you have a sense resistor, which will be a, let's see, a 100 ohm resistor. Okay, so and then this 100 ohm resistor is in series with the capacitor. Okay, so basically this is the circuit you're going to build. Don't forget the capacitor will connect to the ground. And you say there is a RESR, so that's the internal resistance of the capacitor. In the measurement or in the circuit you're going to build, you can ignore about this resistor. Okay, so you don't need another extra resistor. This is just the internal resistance of the capacitor. So as you know, every capacitor in your lab case is the real capacitor. So it's not the ideal capacitor. So it has some resistance. All right. So after you build this circuit, remember you can ignore about RS. Okay, RS is still the internal resistance of function generator. Since you don't have, you are using AD2, there is no internal resistance. So there is no RS. Okay, so after you build the circuit, you're going to use two channels. Okay, you can use channel 1 okay, to measure the input, and then use channel 2 to measure the output. Okay, so the output will be the voltage of the capacitor we see. So if you see the step number 4, okay, or the question 4, use the function generator to generate a 0 to 2 volts square wave at a reasonable frequency. What's the meaning of a reasonable frequency? Is you want your frequency small enough so that capacitor can fully charge. Okay, so after you measure the voltage, okay, so you will see something like this. The plot will be something like this. This square wave is your input. So for example, you use your channel 1 to measure the input. So the square wave will be your input. And then this curve here, that's the output, or that's the voltage across the capacitor. Okay, so that's the step response. Okay, so you are going to use this curve to measure to calculate the capacitance. Okay, so the reason we have this curve is when the capacitor at start, the capacitor is like empty. There's no charge inside the capacitor. Then we apply a voltage start here. Then the capacitor starts to charge. But when the capacitor starts to charge, it's not like charge immediately. It takes some time, and also the charging process, the voltage is not linear. So we can use that property to calculate the capacitance. Okay, so this will be the curve that voltage crosses the capacitor when it's charging. Okay, so if you already checked the lab manual, you should know this when you have the time, what's the time constant? Okay, when it comes to here, we have time constant tau. Okay, so what's the time constant is when the capacitor charge until 0.632 Vs. Okay, so in here, Vs is 2 volt. So which means when you have this plot, when the capacitor charge until 1.264 volt, that's the timing to charge is the time constant tau. Okay, so then you can use further to measure the time constant. So here is explain why you want the frequency small enough. If the frequency is too high, the plot will be something like this. Okay, so the capacitor cannot fully charge, then the signal go to zero again, then the capacitor start to discharge. So the capacitor voltage can never reach one time constant. Okay, can never reach the 1.264. So you want to make sure your plot or your frequency is small enough so the capacitor can be fully charged. And what's mean fully charged, you can say your capacitor voltage finally should be close to the input voltage, something like this. Then that means it's fully charged. Then you can measure the time constant, and after that you can use this equation. So tau equal to the total resistance times capacitance. And the total resistance is just the internal resistance plus the R sense. And you know the time constant, and then you can simply calculate the capacitance. Okay. So that's how you measure the voltage and calculate the capacitance. And then in step number 10 and number 11, okay, you are going to export the data. Okay, I will show you how to do that later. But you will export the data from the AD2 and compare the measured voltage with the ideal graph. Okay, so the measured data is the data on your waveform oscilloscope. Okay, so this is the measured data, and then you can use MATLAB or you can use Excel to plot ideal data. Okay, so this is the ideal voltage plus the capacitor, and this is the equation. You can use this equation to do the ideal plot. And after you have two plots, okay, you want to compare the two plots. And as you know, when you do the measurement, you export the data directly from the oscilloscope, the plot will be something like this. Okay. So this is the voltage across the capacitor. And when you take the data, you want to start from zero. Okay, when you want to start from zero, in that case, when you have two plots together, you can compare them with each other. Okay, if you don't plot at zero, start at zero, what you will have is, so for example, this is the ideal plot. But if you don't plot from zero, maybe you start from here, then what you have is something like this. Okay, so you cannot compare the ideal plot and the measured data because you want to make sure they start at the same point. Okay, start at zero. Okay. After, so you can use whatever the software you want. You can use MATLAB, or you can use Excel to plot the ideal voltage and the measured voltage. Okay. So that's task one. I think the measurement is pretty simple. You might need to learn how to plot with, yeah, I think the hard point for this one is like do the plotting. I think some students take some time to use MATLAB or Excel. All right, for the task two, you're going to do the same thing. The only difference is you change this capacitor to inductor. And then you will get the plot. And the voltage across the inductor, the plot is something like this. It's not same as the capacitor plot. Okay, but you are not familiar with how to measure the time constant by this plot. So what you can do is you can use the mass function. So in your waveform, there is a mass function. So you can use the voltage cross the input voltage Vs minus the voltage cross the inductor. You can get this plot. And you are familiar with this plot because you measure this plot in task 1. And then you can get the time constant. Okay. So that's task 2, and then you can easily use this equation, the tau equal to L over R. So you know the resistance, you measure the time constant, then you can calculate the inductance. All right, so that's task 2. Okay, so for tasks, any question for task 1, task 2? Okay. Okay, so yeah, task 1 and task 2 should be not too hard. And then the task 3. Okay, so you're going to use the 555 timer. Okay, so you already grab the equation in your pre-lab. So if you remember in the pre-lab question number 2, you calculate the time for the 555 timer that charge for the VC charge to threshold voltage. Okay, so you're going to use that equation to calculate the R1 and C1 value in this task. Okay, so if you're not sure like your answer is right or not, please check the introduction video. Okay, so that video like show you how to do the calculation. You can just follow the equation the video used. Okay, so first of all, you need to calculate the R1 and C1 value, and the R2 value is already given. So it's a 10K ohm resistor. And as you noticed, so in the real circuit, when you have R1 and C1, you cannot use any value you want. So for example, the R1, since you are going to use the scoop of your AD2 to measure the voltage at the threshold, and the oscilloscope has an internal resistance. If your R1 is too large, that will make the R1 parallel with the internal resistance of the scoop. So that will cause some issue. So my suggestion is that your R1 need to be smaller or equal to 300K ohm. So yeah, if your R1 value is too large, I don't think you can trick the threshold voltage. Okay, so make sure your R1 value is smaller than 300K ohm. Okay, so after you calculate the R1 and C1 value, you can build the circuit, and the component at the right bottom corner, that's the switch. Okay, so you have the switch in your lab kit. It's like a little push button, and when you push it, it's work as a switch. Okay, maybe I can show you what it looks like later. And also the component at most left side, that's a LED, and the LED do not have any resistance. Okay, so to make sure you don't short your output, you want to make sure you have a 313 ohm resistor before the LED. So this resistor you must have that resistor. Okay. All right. I think that's how you build the circuit. And after, if everything is correct, after you build the circuit, and then you push the switch, or you push the push button, you will see your LED turn on for 5 seconds, and then it's turn off by itself. How you can measure the time is turned on is you need to use your channel 1 and channel 2. So you can use channel 1 to measure the output voltage, which is the out pin of the 555 timer. and you can use the channel 2 to measure the threshold voltage. Okay, so for example, this is your 5.5 timer. You can use channel 1 to measure the way out. You can use channel 2 to measure the threshold voltage. And remember, the pin for the 5.5 timer is different with the schematic on the task. Okay, so you need to search the pinout. Okay, you can just Google the pinout for 5.5 timer. All right. Yeah, I think that's it for task 3. Just remember how you can show this task is work is you want to make sure you measure the output voltage and the threshold voltage by the oscilloscope. And remember, when you measure the voltage, you want to use row mode. Okay. So remember, use row mode to measure the voltage. Okay, any questions? Okay, if no question, let me show you how to export the data really quick, then you can start the experiment. Let me share my screen. Okay, so for example, right now you open your AD2 and you open the scoop. Okay, so I don't have anything connect, but what you have on this screen should be something like this. Okay, and then you click here. This is where you can export the data. Okay, so you say this is the time, so that's the x-axis, and then this is the voltage for channel 1, this is the voltage for channel 2. Okay, so then you can save the data. Okay, it will be something like a Excel voltage, Excel format. And okay, so you save it. And then you can open it by Excel, and then you can plot it. Okay, and you can either use the Excel to directly do the plotting, or you can use MATLAB to open the Excel data to plot. All right, so yeah, that's the task 1, and let's see anything else we need to go. No. And let's see, and just remember when you do the measurement for last task, the timer circuit, you need to change this to row mode, okay, which is the shift mode. All right, I think that's it. Okay, by the way, I want to show you the switch, what the switch looks like. This switch. Let me find one in the lab kit and I can show you on the camera.
Yeah, it's not. I mean, I guess I'm wired, but.
You should have LED.
Yeah, what's wrong? That's all the fucking.
Yeah.
We just gotta make it on.
Okay, so give me 1 second. So the LED, for the LED, you're going to have is something looks like this. So this is a LED. I think you should have this in the lab kit, but it seems like I checked 2 of the students in the classroom, they don't have the LED. You have LED. Okay, it seems like I don't know why you don't have the LED and also the switch in your lab kit. So what you can do is for this circuit, for the switch, if you don't have the switch in your lab kit, you can just use the jumper. Okay, so after you build this part of the circuit, you put the jumper like so. So how the push button work is when you push it, is connect and then it's disconnect by itself. So you can just mimic this function by yourself. Okay, so we can use a jumper and you plug in and plug out. So that's like a switch. Okay, so that's how the push button works. So which means you can connect some jumper from R2, from this node, and connect to ground, and then disconnect by yourself. So you manually make a switch by yourself. Okay, and if you don't have the LED with you, try to use the light bulb you used in the I think previous lab. Okay, to check is the circuit work or not, and if you yeah you can, yeah if you and also you can use the oscilloscope to measure the way out and the threshold voltage. Okay. Yeah. 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 That's it. And if you have any question, just let me know.
Yeah, the circuitry.
Well, yeah, you can start your experiment.
That's all from me.
I think they had these in a separate smart box.
Where's the proof of that? Yeah. This box.
I think it in this box. Yeah, you're gonna be on it. That's one of these. So,
There's.
then small packet.
Probably have one for you if you do this.
Okay, so let's say for the LED in your lab kit is not in the large box. Okay, it's in the separate small bag. Is something like this. Okay, so you see the color, the different color component here. So that's the LED. Okay, you should have separate box in here on the push button. Okay, or the switch is in the same bag of this bag. Okay, so you see this little black thing, that's a push button. If you click it, so that's how you push the switch. Okay. Yeah, remember this should be in a separate small box of your lab kit. Or the also have.
So is the one we have our sense or our sense? Okay. So we don't do
Yeah.
And so there is a question asking about the RESR. So you see here, the RESR is 8.2 ohm, 8.2 ohm. So that's the, as I mentioned, that's the internal resistance of your capacitor. So you will include that capacitance in your calculation, but actually you don't build that capacitor. Okay, so that's just the resistance inside the capacitor. Okay, so you can ignore this resistor when you build the circuit.
We don't have big control.
So that's just the internal resistance of the capacitor. So you don't need to worry about the in the circuit. Yeah, just capacitor.
Okay.
Also, you don't do that.
No, because it's like the resistance of the capacitor.
Yeah, so the 8.2 ohm resistor is the internal resistance of capacitor. So ideally, well, the capacitor is just capacitance, okay? But in the real world, the capacitor have some resistance. Okay, so that's the 8.2 ohm resistance.